Hello all. So in this video we'll be starting with ANOVA test, which is nothing but analysis of variance test. So just let me write it, that it is analysis of variance test. So that's why it is called ANOVA test. So analysis of variance. It goes like this. So firstly, let me talk about what is the need of ANOVA test. So as we already seen that t-test that we have seen before is good for comparing just the means of two populations, right? It is we are given two populations, we'll take samples from that and we'll have some hypothesis testing for that population means whether they are equal or not, but they are just two different populations that we are given. But what if we have more than two populations, like 3, 4, 5? Then this will be a complex task, isn't it? So that's why what we do is we do analysis of variance test. So what we do in ANOVA is that here our null hypothesis, which is H naught, will be, do the means of the samples differs more than you expect. So we will be having, let's say, x1, x2, x3, x4. We have four different populations. So we will find mean of all these populations, mean 1, mean 2, then mean 3 and mean 4. And our null hypothesis will be that whether all these means are equal or not. Right? So it should not be like the means of this sample should differ more. Yeah, so this is the basic motivation behind the need of ANOVA. Now let's start with the brief introduction. So suppose that we have been provided samples of size n. So please note that we have been provided samples of size n from m distinct populations. So we have total m distinct populations, and from each population we have the samples, and let's say we have n number of samples. And what we want is we want to use this data to test the hypothesis that whether this m population means are equal or not, right? So I hope things are making sense because you followed my previous lectures as well. So I'm assuming that my previous lectures are being followed so that you are familiar with the terms like population, sample and so on. So now, as you will see in many books, that analysis of variance are of two types. First is one-way analysis of variance and other is two-way analysis. So why it is called one way and two way? So it will be clear by this point that why this is called one way, because since the mean of the random variable depends only on single factor, namely the sample from which the variable is taken, right? So the sample the variable is from, the mean depends on that only. And that's why this scenario is said to constitute a one-way analysis of variance. But stay tuned, we'll see two-way analysis as well in this video lecture series. So this is just a brief overview that what we are gonna do. Now the important note is that we'll assume that the data that is given to us are normally distributed with the same variance sigma square. But of course we don't know what the variance is, but we just know that the variance is the same. Now let's talk to our approach. In next lecture I'll be giving the more detailed way, but in this lecture will be the brief overview. So the approach will be like, for testing our null hypothesis H naught, what we need is that, so let me just read it out, that ANOVA approach for testing our null hypothesis concerning multiple parameters relating to population mean is based on deriving two estimators of common variance sigma. So whatever variance is that there, we know that it is common to all the populations that we have. Obviously we'll have more than two population here. So whatever m number of populations we have, the variance for all of them is same, even though it is unknown to us, but the variance is same. Now the ANOVA approach for testing this, what it says is that it is based on deriving two estimators of the common variance. So this common variance that we have, we are gonna derive two estimators of this common variance, and the entire theory revolves around estimating this two common variance. So what we do is, sorry, so the first estimator of the two is a valid estimator of sigma square, irrespective of whether the null hypothesis is true or not, right? So we'll derive how we'll get the first estimator and the second estimator. So first estimator just says that it's the estimator of sigma square, that is our variance that we don't know, but we know that it's equal for all the population. So irrespective of whether our h naught is true or not, so we'll accept it as our valid estimator. But the second is like it will be only valid when our null hypothesis is true. So what, in summary, this is the summary, right? Is that when h naught is not true, this later, I mean second estimator, will tends to exceed sigma square. So because when second estimator is valid only when h naught is true. So here I am saying that when h naught is not true, then our second estimator will tend to exceed our sigma square. So it will estimate sigma square, but it won't be exact. It will exceed. And I'll show you the proof that why it always exceeds. Why it's not like it's always less than. It can be less than as well, but it will always exceed. And thus, the test will be to compare the values of these two estimators. So what we'll do is we'll have first estimator of the variance, we have second estimator of the variance, and we'll compare this two value. And simply how we'll compare? We'll compare it by just taking the ratio, and we'll take the ratio of second is to first, because we know that when our h naught is not true, our second is exceeding, right? So when this ratio will be sufficiently larger, obviously we'll be having our significance level alpha in our question, which will be given as of course. So what we'll do is we'll calculate this estimators ratio, and we'll calculate the f value from alpha from the table based on the significance level and of course the degrees of freedom, right? So we'll see the table value. I'll show everything with a detailed example, so don't worry. And after that, if it is sufficiently larger, so basically we'll compare the two values and then we'll decide how to do it. So this is just the brief overview, just don't get dive into it. But the entire idea revolves around like we need two estimators of our variance. So first is the valid estimator irrespective of our null hypothesis, and second is valid only when our h naught is true. And what we'll do after finding these two estimators, we'll take the ratio of it, and whatever number we'll get, we'll compare it with the value which we get from the table based on our significance level alpha and our degrees of freedom. So we'll see all these things in detail, what are the degrees of freedom and all. So don't worry, the very next lecture will be for that only. And then based on that, we'll decide whether we have to accept our null hypothesis or we have to reject it. But so the ultimate task now will be to have two estimators. So this slide shows the brief, like we are rushing towards this estimator findings. So we'll need something called as chi-square random variable. So let me just give the brief overview regarding what chi-square random variable is in this chapter. So chi-square random variable is that, let's say we have n independent normal random variables having possibly different means, right? But the variance should be common, right? So there's a possibility that the means can be different, no worries, but variance should be common, sigma square. And let's say that the expected value of each random variable is given by mu I for all of the independent normal random variables. Now, since the variables, this is zi, as we know that from our central limit theorem, that whenever we'll subtract the mean from the random variable and divide it by its standard deviation, then this will be, the new random variable zi will be standard normal distribution. Okay, this was just the normal distribution, but this will be standard normal distribution. So it follows from the definition of chi-square random variable that the summation of zi square for I belongs to 1 to n, that is for all the random variables that we have, squaring it. So it will be like this, because we'll just substitute the value of zi from this above here. So the chi-square random variable says that when we have something like this scenario, that we have n independent random variables, normal random variables, we'll subtract the mean and divide by standard deviation, and we'll get standard normal, then we'll get square, and that's why it is called chi-square, right? So this is called chi-square, and this is the definition of chi-square random variable, that this summation of squared, that is xi minus mu I squared divided by sigma square, is a chi-square random variable. And of course, one important thing is that with n number of degrees of freedom. So d of f is degrees of freedom. So this was just the introduction of chi-square random variable, and this will be needed to estimate our two estimators of our common variance. So ultimate task is to have the estimators, and we will start from this point in the very next lecture. Thank you.